Good evening, everybody. Thanks for coming out for our speaker tonight. This is the last of our fall speaker series, and all of these have been relating to our Maine Marine Fair Conference. So tonight we have Dr. George L. Jacobson here with us, and oh my goodness, I'm so sorry, that is my phone? Sorry about that. Okay. Let's continue this. And I'm going to read it so I don't get it wrong. But George L. Jacobson is Professor Emeritus of Biology, Ecology, and Climate Change at the University of Maine. Since his arrival in Maine in 1979, he has been a member of the Climate Change Institute, and he was director of the Institute for nearly a decade. His scientific research has focused on long-term climate variability and specifically on forest responses to climate changes during the past 60,000 years. Professor Jacobson's projects have included sites in North America, South America, and Europe. Among other things, he has served as an outside advisor on climate to the European Science Foundation and to the Finnish Academy of Sciences. From 2008 to 2014, he had the honorary designation of Maine State Climatologist. And I'll hand it over to you.
Yes. Thank you.
These two events just reminded me, I was at a chamber music concert we had on campus a couple of years ago, and a violinist lady was standing up there, and fortunately between pieces, the phone went off. We'd all been warned it before the concert, of course, to turn ours off. But it kept ringing, and then she said, "Oh my God, that's mine." I was waiting. So that was pretty fun. But it can happen to all of us. Well, thank you all for being here. I'm honored to be asked to speak. Some of you, I hope, were any of you here for Sean Burkle's talk this summer?
Yes.
Okay, anyway. Sean is a young faculty colleague of mine who took over after me as part of his job being a state climatologist, and he's just a super guy. And I'll show one or two things related to his work. But what I'd like to do in the next 4 hours, they told me I had so long, is give some of the perspectives we've learned in our research, and I mean collectively in our institute and even in the general fields that are involved, over the past number of decades. And the reason that I'd like to do that is that I've learned for my own sake, and then also talking with others, that having a longer-term perspective really helps us all to understand what's happening now. It's we have our own life experiences of a few decades to many decades, and we have historical records going back a short distance, but really, unless we understand the longer patterns, we don't understand anything, it turns out. And it turns out that one of the things that has happened in the kind of research going on in our institute is that we've been focusing on understanding things like ice ages and what causes them and how fast can climate change under the natural systems and so forth. And so I'll get into some of the things we've learned about those things because they really do inform our understanding of what's happening today. And some of the, as I say here, the clues that we can learn from the past are really interesting and fun, and I think help us understand what's going on. Now, in about 3 years, we will have the 50th anniversary of our institute's formation, which was in 1972. This turns out to have been probably the very first climate research institute at any university in North America that was set up this way. And ours was specifically set up to have not just focus on climate, but to have multiple disciplines working together. So we have several kinds of geologists who study, the history of glacier movement, glacial geologists. We have people who study modern behavior of glacier and how ice flows, the physics of ice. We have archaeologists, biologists of several kinds, myself being one, historians, oceanographers, climate modelers, and so forth. And collectively, we work together on our own problems, but often combined on a given problem, and certainly learning from one another as we hear each other talk about our work or hear our students talk about their work. We're able to learn so much, and it's been a fascinating place. Right, it started off with 10. I was the 10th person hired as part of an original plan that was set up in 1972. I came 7 years later. Now we've got 40 people in Maine, mostly on our campus, associated with our research, and many colleagues in other universities. And this map, which is an interesting projection here, is one that just shows, you know, the world in a way in it. And each red dot shows a place that some faculty or staff or graduate student or even undergraduate student has been involved in research over the past few decades. And in other words, it's all over the earth, which is really quite neat. You know, there's a lot to do studying in Maine, but for reasons that we'll see, having a global perspective on all these things really matters. And we don't have an official statement as an institute of this, but my version of what our purpose is to understand the natural variability of the Earth's climate and what kind of forces drive that variability. And why is that important? Well, I think anyway that unless we understand the natural sources of variability and frequency of variability and patterns, how can we possibly assess what's happening today? We can't. And so this is what it's all about. And I'm going to, over the next bit, offer you for some perspectives on time periods ranging from a few decades to 600 million years. And it's a lot to deal with in one setting, I grant. But I will try to weave it together in a way that gives a perspective that I hope you'll find useful. I invite all of you to ask questions along the way. If you would like me to stop and explain something or ask a question about it, please do. We have plenty of time. And otherwise, I hope afterwards we can have a good discussion about questions and discussion about anything that interests you. And I've been looking forward to this a lot. I mentioned that we have faculty, staff, and students traveling over the world. We've had a lot of researchers in Antarctica over the world, over the years, trying to understand how that huge ice sheet behaves, same in Greenland. And this is a photograph from just 2 years ago, or last year actually, of one of my faculty colleagues, Brenda Hall, who's just a brilliant glacial geologist she's from Maine, went to Bates, came to the University of Maine, and now she's a famous faculty member here, a geologist who's known all over the world for her work, and she's with 2 grad students and 1 undergraduate student just getting off the plane in Antarctica for their work. And it's pretty cool. I mean, I don't mean it that way, but the fact that we can have our students traveling and participating, even undergraduates, with our researchers in places like this, it is really exciting, and it's fun it changes the lives of all these people, of course, because ever after they have a different perspective on who they are and what they can do in life, as you can imagine. Not all of our faculty and students are females, however, we do have a few males. That was kind of a joke. You didn't respond very well. About 10 years ago, a little bit over 10 years ago, Governor Baldacci, who was in office at the time, came to us in our institute and asked us to do a study of the future of Maine's climate and to look forward to the end of this century, to the end of the 2000s, the 21st century, and to try to make a reasonable estimate, recognizing that it's a projection forward, but what would be a good estimate of the kinds of changes in climate that might happen here? And then given that, what would happen in Maine? What would that mean for Maine's forests and lakes and streams and the Gulf of Maine? Because all of those things are so critical to our natural resource-based economy. And so being Maine, of course, there was no funding for this. So, but I was able to pull together about 75 colleagues who volunteered their time and expertise, not to do new research, but just to help us understand from their perspectives how these things might change. And we used the best available models of the future based on physics and so forth, and took a conservative estimate. This is not a high-end estimate of how much warming might happen, but even a middle range estimate takes us to a place where by the end of this century it would be probably anywhere from 4 to 8 or 9 degrees Fahrenheit warmer in all seasons in all parts of Maine. Now that's quite good. I mean, that's a significant change. And some of the models, assuming larger amounts of carbon going into the atmosphere, would give much bigger numbers than that. But we took the assumptions we made were that actually humans might actually respond to this and try to reduce carbon emissions. And so whether that will happen remains to be seen. But that was what we did. So we took really a very reasonable estimate and then saw how it changed. And we published this report, which is available. If you go to the just Google Climate Change Institute, you'll find our website is full of really interesting things about research going on all over the world. But it's possible to download this report and several other reports, including the one Sean Burkle brought that's focused on coastal issues when he was here during the summer. But this report is only 73 pages long. It's well edited, and there's some really fine illustrations. And it's printed in it's available as a PDF file. It's easily downloadable and readable. So if you're interested, I strongly urge you to look at it. We did an updated version of this, just a short version in 2015, because people were already noticing changes that were taking place. We've seen all kinds of things that you could name about how the plants and animals that are around us are changed in that time, the spread of ticks and Lyme disease, all those kinds of things. And so we thought it would be actually a good idea every 5 years or so to have an update and just document things that were changing. So the 2015 report is available also online. We're working right now on the 2020 one, which will come out next year, obviously. This is the Coastal Maine Climate Futures that Sean Burkle and Paul Majewski, our current director, produced a few months ago. Now, Maine is an interesting place. This is one of my favorite maps describing what Maine is. A colleague of mine once, when we were hosting an international scientific meeting here in, down in Northport, asked me for one map that shows Maine's climate. And this is the one I chose. And that's because this is the plant hardiness map. Most of you have gone to garden centers and you know that shrubs and trees and things have little slips up down there that say it's zone 5A or 6 or something. So you know something might survive on the coast, but don't take it to Oregon because it won't make it there. Things like that. Now this is the one, the latest one. It came out in 2012. And what it shows is how extremely cold are the winters. And this is what determines a lot about plant distribution. It's what kind of cold plants can survive. It's not the only thing, but it's an important thing. And so all these zones listed here, this is a USDA map that came out in 2012, updating one that had been published in 1991. It was already out of date by about a whole zone in that 15 years, so that's pretty interesting. Or, well, more than 20 years. But anyway, this is the 2012 one. Maybe it's changed already. But we know, all of us in Maine are very familiar with the fact that we've got a huge contrast between the coast, which is so strongly influenced and moderated by the nearby ocean, and then the inland continental climate up in Aroostook County, which has a climate much more like Minnesota or Montana than it does southern Maine. And so this contrast is really interesting, and we all recognize these things. We know the coastal ability to plant, people can plant all these different plants and so forth. But this one I think is really interesting. And one of the things in this little 4-degree latitude state of Maine, we think it's pretty big for New England, but it's a pretty small state by national standards. 4 degrees is all this is. We go all the way from extremely cold continental climates to very mild maritime climates in York County and around Portland. And what does this mean? Well, it's actually striking because this is one of the figures from our 2009 report. And it illustrates literally the spread of the main climate zones across Central and Northern Europe. And so what we have here, or this yellow band, if you can follow it up here, is the change from the northernmost part of Maine to the southernmost part down here. So the northernmost part of Maine resembles in its climate and in its biological features, ecosystems, peat bogs and things like that are just like the ones in northern Finland, up in northern Maine. The ones in the south are just like the ones in southern Poland. And that's because the climates are the same. And so 4 degrees of latitude in Maine is translated to 20 degrees of latitude in Central Europe. Isn't that fascinating? And that's one of the reasons that we have such incredibly interesting ecosystems in Maine and such high diversity of ecosystems in Maine, because we have this compressed gradient because of the strong maritime influence here and then the cold continental air coming across from central North America and Canada in the northern part of the state. And we're sort of spoiled. As somebody who taught climatology class and field trips out every week with my classes, you know, in an hour or two drive, we could be in some fabulous place in a huge contrast from the last place we were, and most dates that would be impossible. So, but this is really interesting. And if I go to the next one, here's the national plant hardiness map. And if we look at Maine, I have to put a little box around our 4 degree of latitude Maine. And that's the same variation in conditions as northern North Dakota to southern Kansas. Who would have ever thought? Isn't that interesting? And I mean, obviously they're different in lots of other ways, but this is the climate picture. It's really a fascinating thing. So this gives us in Maine a chance to have a perspective that's much broader than people in most states have, or there are only a couple of climate zones really. Now, I know when Sean Burkle was here, apparently most of you didn't hear him, he talked about what some of the changes in the last century or so. And this is a photograph of a newspaper article from southern New England, showing that this is 1905, and most of the southern New England harbors, even, not southern New England, not northern New England, were frozen and ships couldn't go in there. Now that does not happen now. In fact, it doesn't happen here now. And here's a photograph of Vinalhaven, which is just not 2 miles from here, about a ferry ride from Rockland that many of us are familiar with. And in 1918, that whole harbor was completely frozen up. And those things do not happen now. And there are interesting stories. There's some of you have probably been up to Cranberry Isles of Mount Desert. And there's a granite building that houses a museum out there in one of the cranberries, I forget which. And the granite blocks were brought out from the quarries in Somme Sound, but they were brought out to the island on sleds on the frozen ice. Wow. Isn't that amazing? I mean, there's no such thing remotely happening now. So this is really a different time. Now, if we look at this, is some data prepared as part of the state climatology work by Sean Burkle. If you're interested, go to the Maine Climate Office website. Just Google that, Maine Climate Office. And among other things, you'll see this, which is a variation in Maine's climate year by year for going back to 1895 up to now, or a year or two ago. And what this shows, of course, is lots of annual variability, and we expect it. We know year to year we have a warm winter, a cold winter. Some years I can play golf in January, and sometimes I can't play in October. And that happens. And there's a lot of this variability, but if we look how this trend relates going back to the baseline, which is just the average of the previous century, the 20th century, there isn't too much doubt about what's going on, is there? And this is just measurements in Maine. Nothing, there's no interpretation needed, really. But some of these really cold periods here are years when the days would freeze, and some of those actually are related to things like volcanic activity on Earth, which for a year or two will cool the atmosphere, prevent the sun from getting down, and lead to cooler winters for just 1 or 2 years. But so some of those can be explained by single events like that. But the longer trend, of course, is related to things we now understand as things that are involving, in part, human activities as well, and not much doubt. So we'll talk about all of this a little bit more. This is from...
Let me interrupt you on
Sure.
the topic of volcanic activity.
Yeah.
Is there a reduction in volcanic activity over the
No,
more
it's
recent
the same.
decades?
No.
Nothing like
It's all the
that.
same. And going back in time, once in a while, we've had some pretty big events actually in recent decades in various parts of the world. But it's just that one way to look at this is here's the variability year to year to year, but the trend on that variability will never stop either. It'll go into the future, even though we can't model it because we don't know which year is going to have a cold winter or a warm one. And you know, I bet in 2035 there will be some winter, or 2030s there will be a winter where it's 40 below in Aroostook County. But that doesn't mean it's not this kind of trend. And so this is what we're seeing. This is why this is so interesting. We're seeing, you know, annual variability related to things like volcanic activity and or possibly some things related to ocean currents that happen locally. But the trend is pretty unmistakable. We just do not have any winters, anything like this, even though we've certainly had volcanoes and other things going on. And even back here, it wasn't that there were volcanoes all the time, it just wasn't as warm. The climate was not as warm. And this is not just Maine, this is lots of places. So that's a good question, though. Because all those things are, and we have people in our institute studying volcanic activity by looking for volcanic shards in ice cores, and they're able to pinpoint where they are when, and have logs going back, and be able to match up something that happened in 1787, and sure enough, it was colder in Europe or something like that. But, and going way back beyond that, where there really aren't even many historic records to compare. Now this is another website that was created for presenting data and information, in this case, current data. It's called the Climate Reanalyzer. And I'm sure Sean talked about this, but this is another thing to Google. It's just, you can also get it, all these things are on our website as well. The Climate Reanalyzer is a site that's now used by thousands of people all over the world every day. And this is a map I could bring up today's, but I won't right now. This is a map for today's conditions, and it shows, we can look at all these things, you know, latest information, the 2 meter above the surface temperature, and then 2 meter temperature anomaly, which means what is the difference between the temperature today and what would be expected based on long-term averages for that area, whatever it is, this is January 7th. Well, I put this one up. It's interesting because, I don't know if you remember, but in the January of last year, 2008, we had a really cold stretch. It was really cold, and all over eastern North America. It was cold, and the news was all about it, and we were talking about polar vortices and all that stuff. Remember those figures we'd see on TV and in the New York Times and places about the polar vortex and that big purple sweep coming down from the north? Those were pictures taken off the Climate Reanalyzer. They also University of Maine Climate Change Institute at the bottom. And it's used all the time by people all over the earth. So this is, and you can play around with this website for a long time. It's the coolest place to follow data. It has the future forecast for everywhere. It's all based on Google Earth, so you can click on this and roll around and look at China or Antarctica and get access to weather data from the past for all of them. It's an amazing site. And everybody, all the climate people are using it just because it's so handy. But this is an interesting one. And the reason I want to point this out is this was a really cold week in January by comparison with expected standards. So even in Maine, it was much colder than January would be, which is already pretty cold, all the way down to Florida. But look at the rest of the world. You know, the rest of the world was way warmer than expected. We were just about the only place that was cold on Earth. And I don't have it right on here, but the average for that day, the Earth was probably 0.5 degrees warmer than average as a whole, even though our little experience locally was that it was cold. And so it's easy to think, well, what happened to global warming? It's cold and all that. But actually, we have to look more broadly at the geographic picture to get a sense of that. And if I have one more example like this. This is this year, back in May. We had a prolonged, cool, rainy May. It was very frustrating for golfers like me. And but it really was. It just seemed like it never warmed up. And you can probably remember some of that. And so here it was, and this is one day, May 21st, and same deal. Look at this here. The central and a good chunk of our latitude in North America was cold, but most of the rest of the Earth, especially including the high latitudes, were extremely warm. Greenland, the Arctic Ocean, even in Australia, which was in its summer, And so, in fact, the whole Earth was almost half a degree Celsius or 1 degree Fahrenheit warmer than expected for the day, even though, again, we were having this kind of miserable weather. So it's just the contrast between, this is the interesting point about the difference between weather and climate. Weather is what we have on a given day. Climate is what we would expect to have based on long-term measurements. So I'm going to stop with that. Now, let's get to talking about, before we get into more, let's talk about just facts, what we know about how humans are interacting with climate right now. We know that huge amounts of fossil fuel have been used, and that has led to CO2 and methane going into the atmosphere. By 7 years ago, we had added, and this is easily known because we know how much fossil fuel was burned, it's all economic data. We had added 500 billion metric tons of carbon to the atmosphere, and by 2050 it'll be double that at least, because we're actually putting carbon in the atmosphere faster than the estimates of that time were. But these are just data points. It's a matter of physics that greenhouse gases trap heat. That has to do with the way those molecules, CO2 molecules and methane molecules, but CO2 in particular, vibrate when long-term radiation, that is infrared radiation, is radiated back. The sunlight energy comes in short wave radiation, it's absorbed by the Earth and then radiated back as long wave, the kind of heat we feel from a pavement or something like that. And the greenhouse gases trap that long wave radiation and don't let it get back into the atmosphere and out of the Earth. So that's sort of why it's called a greenhouse gas. But these have been known for quite a while, and there's no doubt about this, the physics of it is crystal clear. And so the combination of these things mean that the Earth has to get warmer. I mean, there's no way around it. Unless the laws of physics are wrong, and probably they're not. Somebody I was asked by a legislator once, about 10 years ago, well, what if some scientist discovered that the laws of physics were wrong, and would they try to hide it so that they could keep getting grants? And I said, are you kidding? He said that person would get the Nobel Prize so fast they wouldn't even make their head spin. Degrees probably so. And then one result of all this is that the amount of sea ice in the Arctic has been decreasing, and glaciers have been melting, not just Greenland, but mountain glaciers all over the place. And these are all, of course, you read about all these things in the press all the time, and you hear a latest version of all this. And we talk about sea level rise, and that's something we can expect based on how much glacial ice is melting. The ice, it isn't melting sea ice that matters, it's the glacier ice on Greenland or in the mountains or Antarctica that decreases. Any of that terrestrial ice that comes off and melts and goes into the oceans is what causes sea level rise. And the amount of ice leaving is, right now, I can tell you, so much faster than anybody thought even 5 years ago. So all bets are off on what the sea level rise will be. But I would say now pretty conservative estimates are that by the end of this century, it might be a meter or two in most places on Earth. And places don't all behave the same way for various reasons, because of the crust bending and various other things. Sea level isn't the same everywhere, even though you'd think it would be. But this gives the idea correctly that this is a serious thing to consider. And in fact, we had a Navy admiral who was in charge of climate response come to our campus about a few years ago. And he said that the Navy's really worried about two things. They're worried about the melting sea ice in the Arctic for national security reasons. Because it used to be there was all this ice and submarines would go underneath and keep track of each other, but that was about it. Now it's going to be open to seagoing ships, and it's already happening, and China's got trade coming this way. And it'll, maybe there'll be lots of positive outcomes of that, but it will be changes in you can see why there'd be national security concerns. But the other thing he said was sea level rise, because he said just the Navy has thousands of installations around the world, and they're almost all at sea level. And retrofitting all these kind of places to a meter or two of sea level change is a non-trivial expense and non-trivial activity, really. And that's just the Navy. The whole rest, most of the people on Earth live somewhere near the ocean. So this this kind of thing is going to have broad ramifications. Let me just stop this for a second, if I can. Maybe I can't remember how to do it, but well, anyway, this is sea ice in the Arctic, a reconstruction of how the sea ice has been recorded by satellites. And it started in 1979, 91. Just keep watching this. And the darker the ice here, the thicker it is. And many years, when it's just light gray, it's probably just 1 year. 95, and just keep watching this. It'll take us through a whole series of years. 97, 98, I'll read the years. 98, just keep watching. 99, so we're seeing spring, and summer, and winter as it freezes up again. 2000, and so there's the currents and carrying the ice out in the summer and so forth. So these are the annual cycles, but this is where the ice was and how much there was. 25, 2006, 7, keep watching, 8, 9, 10, 11, 12, 13, 14, 15, 16, might stop there. So look how little ice there is that's more than 1 year old, almost none. It used to be mostly many meters thick of ice because it was many years old. It's starting over again, I won't run the whole thing. But it's fascinating because we're going from, well, here in the early days, you can see how much old ice there was, multiple years of ice, many meters thick. And when we got to the end of it, 1 year of ice, which is nothing. I mean, it takes no kind of icebreaker to drive through that, and that, of course, melts. And if one thinks about it, the more open water there is in the summertime, and I just saw a report this morning. I got the report on this past year's measurement of Arctic sea ice, and it was timely because I knew I'd be here, and it said that this was the third lowest amount of sea ice in all these observations since 1979. So there have been 1 or 2 years less than this, but the amount of old sea ice is disappearing, and what's left is just what freezes up that previous winter pretty much. So this is really an interesting illustration, I think. It's really kind of stunning to watch. Now, okay, let's go back and talk about greenhouse gases and what we know. There's some interesting characters in this story, and I hope you'll indulge me just talking about them a little bit. I've spent quite a bit of time in Sweden, which is the home of 2 of my grandmothers. I have a Norwegian grandfather. But I spent a lot of time doing research with colleagues in Sweden. But I'd already heard of Svante Arrhenius, who was a famous chemist who worked in Sweden in the early, well, a little over 100 years ago. And he had a fantastically interesting career. He went to the University of Uppsala, which is up near Stockholm. And he was in chemistry. And he figured out, started doing research on things that today we call electrochemistry, which are things that have to do with chemicals, how batteries work, and things related to what's now used for electroplating, the interactions of chemicals and electricity. Never been done before. And he finished this work. Now, I can tell you from my own experience being involved in examining students in Scandinavia, what happens is a PhD student in those countries doesn't have a local committee and writes a few versions of the dissertation and then gets tested by that committee, and then they go out with their degree. In these countries, to this day, the students have to finish, write up their report, publish it in printed version. Copies get distributed for something like 2 months to anybody in the field all over Europe. So it's not just your in-house professors that you've been knowing for 4 or 5 years. So these get sent out, and then anybody who wants to can come to the defense, which in Sweden is called a disputation. And the person who does and it's always an outsider, often from another country. I've done several of them. And that person is called the opponent. So it is quite a thing. So anyway, and not only do the people from the university come, but all the family members and childhood friends of all these people come. They're all just much fancier than I am. It's at 10 o'clock in the morning. There are flowers up on the table. And at 10 o'clock, the professor in charge of the department comes out and says that today we're here for the thesis defense of Per Lagergren, and his work is this. And we're very fortunate to have a very distinguished professor, Maria Holmgren from Denmark, come to do be the opponent. And everybody's known this for a long time because it's all set up. And then there's a separate, not the committee members that were the students committee, but other faculty members are selected from that university and others to be the judges of this whole thing. So it's a real public event. And you can imagine the pressure on the students. So then it's interesting. I couldn't even digress on this, but it's just interesting. So the student doesn't get up and give a seminar. Typically here, the student will give a half-hour, 45-minute seminar about their work, and then there'll be some questions, and then the committee and the student retreat to somewhere and ask a bunch of questions. Here, the student doesn't even talk about the work. The opponent does. The opponent gets up and, having read all this extensively, having it for several months, the opponent, he or she, will stand up and say, this is a very interesting piece of work dealing with such and such. Now, the opponent is recognizing that most of the people in the audience have no idea what this is all about. They're friends, family, people from different departments and all of this. And so the opponent does a good job of setting the scene in the big picture and why we need to do this kind of research. And he said this is really an interesting major contribution to our field, and he did show these kinds of things. But then after about 15 minutes of that, the opponent says, but I do have a few questions. And so then the opponent and the students sit up on the stage at a table with the flowers all around them. And for 2 hours or more, the opponent asks questions. And it's something, because of course the student always should be the world expert on what their dissertation's about. And most of the time it's actually really great, because they're able to demonstrate that they're sitting up there with this famous scientist from somewhere else, and they can have this high-level conversation and hold their own, and it's just what one would want. Once in a while it doesn't work out so well, but anyway, the reason I tell that is, Arrhenius was doing work that his own faculty members in his department thought was just crazy. They had no idea what he was doing. They thought it was nonsense. But he demanded to defend, so he published it and sent it out. And they had his defense, and they reluctantly passed it, put it that way. They decided, well, we probably won't go out too much, but we'll pass it. Well, weren't they surprised when, 1 or 2 weeks later, all of a sudden come the most famous chemists from Germany and Switzerland and France coming up to see this guy? Because they had gotten the thing and they knew that this was an incredible breakthrough in all of chemistry. And so, about 10 years later, we got the Nobel Prize for Chemistry, and went on from there. Well, and so all these fields of batteries and electroplating and everything are derived from his work. And any chemist would know all about it. But what's interesting is he started thinking about, he wasn't the first one to think about greenhouse gases. Somebody else had done some quick calculations. Now you have to remember, this was very early in the Industrial Revolution when fossil fuels were being used for steam powering, coal was being used for ships and trains and things like that. Electricity wasn't being produced or anything. But he saw that this was potentially going to be problematic. As we added enough carbon to the atmosphere, it had to make the Earth get warmer. And he started going around Europe giving talks for about 10 years. He just almost set aside his career and went around trying to tell people this is going to be serious. And he called it hothouse Earth and things like that. What's interesting is, of course, he thought it would take 500 or 600 years because, nobody would have any idea the rate at which we would put carbon in the atmosphere. But he did that. Then after that, he went into epidemiology and had an extremely important career in epidemiology. So quite a guy. But I like telling this story because it encourages all of us, really, and especially students, to realize that we should stick to our guns. When we know something and people aren't understanding it, we need to figure out a better way to explain it. But we shouldn't give it up just because people tell us, oh, you've got to do something else. He didn't give up, and he changed the world in many, many ways. Another example is a fellow named David Keeling, who was a oceanographer out at Scripps Institution of Oceanography in San Diego. And this is a famous curve you've all seen, the increasing CO2 values in the atmosphere starting in 1957. 57 was an interesting starting point, and that was the time because there were no satellites or global observation systems at all at those times. And geologists around the world, or geophysicists, knew that it would be really useful to have at least one snapshot of the Earth for 1 year and find out as much information as possible. And so they planned this. It was called what was it called? Something like the annual geophysical year. Anyway, something that I should remember this, but so they figured out all these things to measure ocean, atmosphere, all kinds of things, temperatures, physics, everything else. And Keeling said, well, we should go measure the Earth's CO2 levels. Nobody had ever measured them before. But if it's true that they're increasing, wouldn't it be interesting to see? And we should go out to Hawaii, where we're out in the middle of nowhere in the ocean and not bothered by pollution of local sources. And that'd be a good place to establish it. So they proposed this to the authorities in the U.S. and around the world, and they said, no, that's not worth it, so don't do it. But fortunately, he did it anyway. So here's another case of somebody who stuck to his guns. He just went out there and put it up. And of course, it took a few years to see this upward trend. And now it's this famous curve that every school kid knows about. And it has this interesting sine wave, up and down, up and down, up and down. What's that all about? Why would it not just go up in a linear fashion? Why each one of these up and down sine wave segments is 1 year? What would make the carbon go up in the atmosphere and then down in the atmosphere every single year?
Well, you're heating in the winter.
So what would that mean?
So you're putting much more into the atmosphere.
Yeah, so, okay, that's
during the winter months.
So then why would it go down?
Absorption in the sea.
Well, that's
In
to
the
be
summer.
part of it. What else happens in the summer? It takes plants photosynthesize. So it's the annual breathing of the Earth. And it's all, the reason it actually isn't a global signal, because almost all land on Earth is in the northern hemisphere. So this is really northern hemisphere plants, and plants taking it out in the summertime and then releasing it, and including fossil fuel in the fall, but releasing it just by fall decomposition of leaves and wood and things that happen right now. As the leaves fall off the trees and decompose, that carbon's all going back into the atmosphere. So it's fascinating many levels, but anyhow, here we are. I've got about 3 hours to go.
But so Brazil's southern hemisphere, and that doesn't have an impact on this. So
Nothing compared to the northern hemisphere, because the temperate levels of the northern hemisphere are almost so much land that it's the forests of the northern hemisphere that really drive this signal. But it is much more complicated. You're right, absorption by ocean water in places, but that would vary. Since both hemispheres are on a phase for seasons, that would sort of be counteracted. And so it is mostly photosynthesis and then decomposition. That's what this really is. Now we know something more than what's happened since 1957, because fortunately it's possible to look at ice cores, and this is a major thing that's been going on at our institute now. When I was director in about the year 2000, we hired several new faculty members who worked on ice cores from Greenland, Antarctica, and places like that. Most recently up on Mount Everest. And interesting. But these ice cores that go back through sometimes thousands of meters of ice and hundreds of thousands of years of time give us a record of what the atmosphere was like in those times in the past, because they're contained in the ice are little bubbles of air from all those times. And it's a complicated story of it and how to measure it and all of that, but it's very sophisticated now. And these patterns, I'll show you several versions of it, show us quite a lot. And here's a record of CO2 in the atmosphere for the last 800,000 years, 8 ice age cycles. And the green record here is the record measured in Hawaii since 1957. The red is overlap between the green and part of another ice core called the log dome from Antarctica, and those correspond exactly. So where the Mauna Loa record overlaps with the ice core record from Antarctica, they have the same. So that's encouraging, because that means the measurements in the ice can be relied on. And then going back in longer records, here the blue one is called the Epicodome C, and these ones go back now more than 1 million years. But anyway, it shows. And the reason I show this is because I put these green bars on this one because they show the natural variability of CO2 in the atmosphere for the last almost 1 million years, and it shows variability from the peak of ice ages at the bottom to the peak of warm interglacials at the top. And that's what it is. And it doesn't really vary beyond those lines. I mean, I could move that one line up a little bit. But clearly what's happened in the last 100 years is way out of line with that natural variability. So this is a pretty striking set of data right there on its own. Okay, now we're reverting back to a different time. And this is a special, I put this special quiz in here for you. And I hope you can all answer it, but I'll give you a minute to think about it. This is a plant that once lived in Maine. It's about life size actually on that screen. That's about what it was, a little over 1 meter high. Anybody recognize it? No. Well, it's probably.
Seaweed?
Is it what?
A seaweed?
No, it's not. It's a land plant. And it was growing upright, standing upright on the land. Well, I'm glad you didn't recognize it too much because it lived almost 400 million years ago. But this is interesting. Now, this is you'll think this is off the crazy, but this is actually, to me, really interesting. I've never heard anybody else use this kind of information. But these are ages called the Devonian sediments from the rocks from the Devonian age extend down to the northern Appalachians, including Maine and up into eastern Canada. And the Devonian was around 390 to 300 million years ago, and it happens that we have quite a few rocks exposed at that age in Maine. There are lots of other ages we don't, but this is one of the ones we do. And there's some places in Maine, especially up in northern part of Baxter State Park, there's a valley, the Trout Stream. There's a trout valley. The formation is the rocks that are there. It's kind of a slate-like rock that peels apart in big flat sheets, and just by chiseling those open are exposed these fantastic fossils, plants. And it's interesting because these plants, this one happens to be, the legislature didn't have anything to do one day, so they said this is the Maine State fossil. So, but I actually think it's a good idea. I'm not making fun of the legislature because I think it's neat that they did this. The state geologist and others helped do this. But this is interesting because these plants were living in Maine and throughout the landscape that existed then shortly after plants and animals came ashore from the oceans. All life had been in the oceans until, a little bit before this. And plants came on land first as sort of slimes that were living on the rocks and things like that. But then evolution took over, and there was an advantage to having vertical structures that could collect more solar radiation for photosynthesis. That's what it's all about. And then that required the establishment of a vascular system to get water up to the vertical surfaces and provide water for photosynthesis, because what goes into photosynthesis? Water and CO2. Remember that? 6 molecules of CO2, 6 molecules of H2O, plus solar energy produce a sugar. That's what it is. That's all photosynthesis is. It creates a sugar that is the basis for all other life activity, plants and animals. And so these plants came ashore, and this is quite interesting. Now notice that these earliest land plants, what is this? It's hard to say what these structures are because now I've told you it's so old. But these look like some kind of fruiting bodies, don't they? Or something, maybe they produce spores or something like that. But what does this seem to be lacking? What's lacking about this kind of plant compared to plants we're used to today? Leaves? Yeah, I agree with that. Well, let's take a look at that question. Now, these earliest land plants lived at a time when the Earth was a very different place. This is about the time the plants were here in Maine. These particular ones, and there are others. It's not the only one. There are many other different types of plants that are represented here. There's some wonderful sites up on the Gascony Peninsula of this thing. This figure with the red curve was created by Robert Berner of Yale University, and it shows how much CO2 is within the atmosphere in the past approximately 600 million years ago. We used some geological sleuthing to figure this out. These are, estimates, of course. But here's today's level, which is plotted at 1. So this 1 equals today's level of CO2. And around 400 to 500 million years ago, it was almost 20 times as much CO2 in the atmosphere as there is today. But what did that mean about the temperature of the Earth?
Warm.
And so these plants had lots of sunlight, they had warm temperatures, and gradually, as they grew and were, but it was also wet, and most of the vegetation at that time were growing in swampy areas. Well, why was that? With the heat being that high, and it doesn't mean it's 20 times as warm as today, it's not a linear function, but the heat was enough that the heat was also hitting the oceans. And what does that mean? Evaporation. So when water evaporates from the ocean and comes over land, that's rainfall, and the precipitation then at many higher levels than we would have today created swampy areas. So these plants were all living in places where they would have wet feet, and when they died, they'd often fall over, get buried. The next plants would grow and get buried, and this is the way it happens in a peat bog today. But ultimately, that happened, and this was the period between about 400 years ago and 300 years ago when the Carboniferous deposits were formed, and that's when all the coal beds were formed, and all of them were formed, almost all in swampy conditions like this. They were peat bogs, where the trees fell over. Now, they weren't trees like ours, they were tree ferns and all kinds of things that would look bizarre to us today, but they were growing massively fast, and during that next 100 million years, when the carbon was sequestered in the ground because of photosynthesis and burial in these bogs, the CO2 levels way down to modern values. Now, it also happened, this was, as I said, this was a very warm winter at this time, and I just said all this, the coal and oil deposits and natural gas deposits were all done at this time. Even on the continental shelves, the productivity was extremely high, and the organisms growing in these shallow ocean waters got sent into the ocean sediments and compacted under great weight over the next few million years, and that eventually turned into natural gas and oil. So all these things created the fossil fuel that we're extracting, really a tiny fraction of it, but enough to be changing the chemistry of the atmosphere. We aren't anywhere near 20 times as high, but we're going to get to 2 or 3 times as high as background in the beginning of the Industrial Revolution. And I just point that out because here, at this period, right here, after this cool period, well, let me talk about that. As the CO2 levels got down to modern values, we know that now it's cold enough that we have ice ages. One question is, well, okay, I forgot an important part of the story. As the CO2 levels fell in the atmosphere through this process of the sequestration and building of coal and oil beds, the plants didn't have as much surface area as they needed to get the CO2 necessary for photosynthesis. So that was the time when leaves evolved. Exactly that time. Leaves evolved through the stomata on the underside of leaves. They took in the CO2, they took water from the soils, made photosynthesis in the leaves as we're used to today. And so that happened. Oops. And then we got most of the coal and oil. Well, here we are 300 million years ago with temperatures on Earth, CO2 levels, and then we can also infer temperatures being quite cool. Well, we know we have ice ages now when it's at this level. What about then? Would we expect to have ice ages? Well, there were. Same reasons. It was cool. CO2 levels were low. It was cold enough. We had ice ages. They're all, at least I know in the records, same kind of signal we see today. And then there were some other natural processes, including some vast volcanic activity that took place several places on Earth that brought the CO2 levels up higher again. And it's interesting because this is the time when dinosaurs were living. You know, they went extinct about right here 65 million years ago when that big asteroid hit down in Mexico, the Gulf of Mexico. But it's a good thing it was this warm because dinosaurs, which dominated life, you know, large life at least, vertebrate life on Earth, were cold-blooded animals. You know, there's some speculation that a few of them might be able to have some temperature control, but mostly not. They were reptiles. And if this had been temperatures like then and now, they wouldn't have, dinosaurs would have not have ruled the Earth in the same way. But it was after dinosaurs went extinct and as the climate keep getting cooler, that mammals then emerged and flourished evolutionarily and led to us and the modern world. All right, now after that long view of time and CO2 variability, let's jump up to the little more recent past, merely 20,000 years ago. This is the peak of the last ice age on Earth and in North America. It turns out it was also in South America at that same time. But this is, I sometimes say this is the first satellite photo of the polar view of the Earth 20,000 years ago, but it isn't really. It's just a reconstruction. But this is a good reconstruction based on what's known by the work of glacial geologists of exactly where ice was at that time. So this was the peak expanse of ice, extent of ice, at the peak of the most recent ice age, 20,000 years ago. And at that time, of course, Maine was well under ice. This was all the way out actually to Georgia's and Browns Banks. That was all under ice. And Katahdin was covered by a lot of ice. There are rocks on top of Katahdin that were brought up from Canada by the ice and so forth. So it's quite a very different world. And we know Maine had to have been covered many times before by similar ice during previous ice ages, and of which there have been many. And in fact, this is a figure based on some ocean sediment records. I won't go too much into exactly how they were collected. But these figures, which can be seen in ocean records, ocean cores taken anywhere on Earth, go back 800,000 years. And the lower times are the coldest times. And the most recent ice age that I just illustrated here with that figure would have been right here, about 20,000 years ago. But suddenly, the Earth got much warmer and led us up into the present warm period. We call these brief warm periods. See, notice how these cold ice ages are scattered along every 100,000 years roughly. But they almost always end with a very abrupt warming to an interglacial and then gradual cooling to the next one and then abrupt warming. Well, we have all kinds of records of this most recent deglaciation and behavior of plants and animals on Earth, and so this is where we have most of our information. I'll just point out, you may have heard the term Holocene. This is the geologist term for the current interglacial that we're in. But there was one about 100,000 years ago, 200,000 years ago. And notice they're all short. They only last 10 or 15,000 years and then descent into the next ice age. But also an interesting perspective that our species, the evolution of Homo sapiens, doesn't even go back 2 complete ice ages. Our ancestors were here, but our species is we're just a blip on the record of time. So this kind of gives an interesting perspective. And having said that, all changes in human activity and civilization that we think about have happened in this little period of warming in the last 10 to 15,000 years. That was the invention of agriculture about 12,000 years ago, which allowed the first settlements to occur. People did not have to be hunters and gatherers and moving around on the landscape very much. They could grow crops, stay put, have large communities. So that required a different kind of social organization. I'm sort of summarizing a whole bunch of archaeology here, but you can see that it has to be something like this. Once there'd be thousands of people living in one place, there had to be mayors and police chiefs and stuff like that. They didn't call them that, but somebody had to do this, and there were, in fact, all over the world where there were aggregations of people happening, because this happened not just in the Middle East, but lots of places. It led to expansions of religions, because religion, there was no understanding of any explanation other than that there might be some gods doing something. So the religions were all developed, and interestingly, I mean, this is really me talking, but they all basically came up with the same rules. We should be nice to each other, we shouldn't kill, we shouldn't steal, you know, and for obvious reasons, it kind of makes it possible to get along and do together. But anyway, I don't want to get into an argument about all that. But that's how I see it. And I think it makes some sense. But that all happened right here. This is just in the last few thousand years all this happened. It's really pretty remarkable. All right, and so let's go on. Now, what do we know about Maine, for example, during this period of deglaciation and expansion of vegetation into the areas where ice was? Well, we know a lot from, in my kind of field, by looking at sediment cores. The ocean cores were taken, ice cores were taken, lake sediment cores were taken, and this is one we took on Sergeant Mountain Pond about 10 years ago. And it is a meter-long segment of core. This is all, it's about probably 2,000 years worth of time. This black-brown mud consists of the remains of algae that lived in the lake, green algae, diatoms, little microorganisms that were living in the lake, plants and seeds and things from the vegetation on the surrounding area, pollen grains that have come in from the surrounding area. And so we have ability to get radiocarbon dates on different depths to do studies of the contents of these. One of the kinds of things that was done in my lab, one of several things, was looking at pollen grains in the sediments. And these are clean, modern pollen grains of things that are common around here, fir and something from the rose family, ragweed. This one is an elm, this one's a grass, this one's basswood, Tilia americana. So anyway, these are all recognizable. We know them because we know what the modern ones look like. So we can look in a sediment core and find all of these and tally how they've changed in abundance through time. And by having radiocarbon dates, we can reconstruct the history of the vegetation on the landscape. And I was fortunate enough to be involved in the publication of some of the first maps. Once hundreds of sites have been studied across the landscape, and we knew not just what happened in this lake in Maine, but ones in Minnesota, you know, Tennessee, Florida, Texas, and so forth. We could then start to make maps in space and time and show how the different taxa changed in their distribution and abundance on the landscape. It was, you can imagine how exciting this was. We had these things scattered on the floor in a friend of mine's house down in Providence, who was a professor at Brown. And we were just looking at them, I mean, we felt kind of like God, because nobody knew it. We were the first people to notice. And it just was so exciting. And one type of tree had this one, another one had a different one, and they were incredible number of different stories coming out at the same time. Well, these are reconditioned maps that were used in the famous Ecology textbook for a number of years. Some of the ones that we produced back then. But this shows the kind of variability in space and time for just these three taxa: spruces, oaks, and pines for eastern North America. The gray pattern is the ice, and you can see how that diminishes through time. These are thousands of years before present. So as the ice disappears, the taxa tend to move up to replace on the landscapes where the ice was, and species like spruce, which are boreal tree species, can move up quite far into the north, you know, in Maine and north. Oaks, of course, are a southeastern group. They were sort of restricted to the Gulf Coast when at the glacial maximum, and then they've spread up, and of course there are many different species that make these up, and they're typical of the forests of the states, those states now. And pines had an interesting history because they were all, none of them were, even the northern pines that live up here now were anywhere but down here in Florida. And we know that jack pine, which is one of the northernmost pine in North America, you know, the southernmost distribution is on Mount Desert Island, but it goes way up into northern Canada and western. And it was growing in Georgia at this time, at the last glacial maximum. That's where it was growing. And you know, all the species that are here today were somewhere, and we can show in these maps how they've changed position. So along the way, the two groups of pines, the southern and northern pines, split, and we can see the southern pines that now dominate the southeast, and the northern, basically three species of pine: jack pine, white pine, and red pine, that occur up in the north, and how those changed in through time. So it's quite fascinating. Now I'm going to do a quick exercise with you so that you can understand something. I'm going to ask you to think about the dynamics of this. I'm going to go through 21,000 years of time quickly and it'll look sort of like a movie, and it'll let you, what I'd like you to do, the numbers are up here, but I will read the years as we go by. And if you focus down here, there's the white area is ice, and the darker the amount of green, the more dense the spruce populations are. They're present in all these places where it's green and gray, but the greener are places where there's more of it. Now, here's the map of the U.S., and Florida looks a little strange, doesn't it? It's not because I can't draw it. It's because at that time, at the glacial maximum, sea level globally was 140 meters lower than it is today. That's how much of the world's oceans were taken in precipitation, left on land as ice. It's a huge amount of water. And what happened as the sea level fell that far, the continental shelves all across the northern part, well, and all around the world were exposed. And the continental shelves are around 60 meters of depth, and they are around Florida anyway. So once the ice on land accumulated enough that sea level fell to minus 60 meters or more, then all the continental shelves were exposed and had plants and animals living on them. And now even fishermen could still dredge up mammoth bones and stuff like that from offshore along the east coast. But that's why it looks like this. You'll see it changes through time. Okay, let's go through this exercise. And what I'd like you to do is follow this and look for times in the last 20,000 years when things stayed the same for a while and when they changed. And we'll discuss it after. Okay, so I'll read off the numbers. I'm going to skip 2,000 years at a time for the first few. So 21, 19, 17, 15, 13, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, today. So what time did it stay constant and not change? Didn't. Isn't that something? The whole time. It was changing all the time. And that's because the climate was changing all these times for reasons related to the 3 solar forcing factors that I will only explain if you demand that I do. But it's fascinating. And if we go back just a few thousand years, the Northeast is interesting. Let's go back. You notice that by 7,000 or 8,000 years ago, there's almost no evidence of the boreal forest as we saw it across the north. There are some spruces here in the Maritimes, but not much here. Not much in Maine. And then gradually, 8,000, if we go to 7, see there get to be more developing here. 6,000, you can see the boreal forest is starting to form itself. 5, but now look what's happened to the spruces populations down here in Maine and New Brunswick. Pretty much, I mean, not that the trees weren't here, but there were nothing that looked like spruce forest that we take for granted today. In northern and eastern Maine, we define as spruce fir forest. So they're not there. 5,000, 4,000. Now look how the spruces, as the climate got cooler and moister, crept down into Maine. 4,000, 3,000, 2,000, 1,000 today. And so it's really just in the last couple of thousand years that the spruces and firs have come into Maine to the pattern we accept today. And actually it's even more than that. These are maps of just our region, Maine and the Maritimes, that were developed as part of her PhD work by a grad student of mine named Molly Schaffler, who actually lives over in Northport. And her work was focused on spruce populations in coastal and inland Maine. And we knew from some of these maps that I showed you earlier that were done in my earlier work that Maine had a recent establishment of spruce, but she looked at it in much more detail at the sites and did especially work along the coast. And it turns out that 1,000 years ago, even though most of Maine didn't have much spruce at all, there was a strip of spruce right along the eastern coast, a narrow strip from a kV or so down towards New Brunswick. And in fact, that strip was there all the way through the last 10,000 years. Her work showed that. Even though in the inland, it was much too warm and dry and there were too many fires, and species like spruce and fir couldn't be there. And in fact, the reason the boreal forest didn't develop in the north until 5,000, 6,000 years ago is that the climate in the early part of this Holocene had been warmer and drier enough that there were lots of forest fires, and the forest fires favored species like pines and birches and so forth, and they show up abundantly in the pollen records, but not spruce and fir. But gradually, as things changed in the Earth climate through these natural cycles, we got to a cooler, moister time. But what's really fascinating here is that her work has shown that, well, it was interesting to see that this narrow coastal strip stayed cool and moist the whole time, and I'll get to why in a minute. But also that it was really only since 500 years ago, oops, let me go back, that the dense populations of spruce and fir in northern and eastern Maine came into existence, which means that what we think of today as those critical defining features of our boreal forest and Maine landscape are only a few generations of trees old. Isn't that interesting? I mean, people would think this has got to be thousands, the forest primeval, and and I could show you different tacks, and each would have its own story, different, because each species' response to climate is different. But it's really fun to put all this together, and I'm just giving you a brief touch at it here. Now, why was the coast of Maine different? Well, this whole eastern part of Maine has a much colder climate zone, according to this map, than, of course, central, the Brunswick area down to York County. And we know that down east Maine is a cool, foggy place. That's no surprise to anybody. But why is that? Well, people who know a lot about the oceans are very familiar with this, but this is a thermal image, satellite image, the darker the pattern being, the colder the water. And what this is showing, that this cold water is, of course, distributed from the Bay of Fundy, and it comes along a coastal current down towards southern Maine and southern New England. And as it comes down the coast, it gradually gets warmer and warmer. Well, as it emerges from the Bay of Fundy and by Grand Manan and things like that, that has pretty cold water, which is why the summers are always air-conditioned in eastern Maine, in that coastal eastern Maine. And you can imagine that's why the houses are in Gouldsboro and Bar Harbor and places like that. The rich people would come here because it was pretty nice. And they didn't have air conditioners in Philadelphia and New York and Boston. And of course, we know that the reason that cold water is there at Bay of Fundy is that the cold water from the Labrador Sea comes around Nova Scotia and New Brunswick and comes up into the Gulf of Maine through this deep channel called the Northeast Channel. And it gets up into Bay of Fundy, and twice a day, because the highest tides in the world are mixing water there, that cold water, which is 4 degrees Celsius or about 39 or 40 degrees Fahrenheit, comes to the surface twice a day and starts its trip down the coast. And it's the cold replenishment of the cold twice a day that has forever, at least in the last 5,000–6,000 years, kept this eastern part of Maine cool, despite the fact that the interior was much warmer and there were fires. It's a really localized thing. And
so it's like an eddy?
Well, it is like an eddy, but I mean, the circulation pattern in the Gulf of Maine is that the waters that start up here come down the coast all the way down to Cape Cod and then around. It's more complicated than that. I could show you a figure of the currents, but this is the general pattern. And that if we go back a couple, this one, it's possible to see here how the water is being heated up as it drifts down the coast past Penobscot Bay and then down towards Cape Cod. But anyway, this is the reason Molly was able to show, well, the explanation, I think, for why that narrow strip of land, and it's just a narrow 15 or 20 kilometer strip of land along the eastern coast, remained cool and had spruces all the time. In some cases, at least for 10,000 years. The spruce never left it, even though it was not present much in the rest of Maine. It's just because of these currents. And these currents are going to continue at Bay of Fundy high tides. 40 feet tides twice a day aren't going to stop. And that's going to keep bringing the cold water up. And so I think no matter what happens in the rest of Maine, my prediction is that property along the eastern coast of Maine is going to be really nice for a long time. And I wish I'd got thousands of acres when I first moved here. But could have afforded it, well, I didn't have any money, but it wouldn't have cost very much then. All right, let's move on. Here, again, so I'm coming back here to a map, a figure we saw earlier. This is just another variation of this map. The blue one is the temperature changes on Earth based on the ocean records, and the high points are the warm times, these little short 10, 15,000 year periods are interglacials. We're in one now, there's the last ice age, the one before that, the one before that, and so forth. And these are on a regular cycle set up by things related to the Earth's gravitational interactions of the Earth and the planets and the Sun. If you want, I can explain it, but it'll take a few minutes. And here we are again looking at this recent rise during which humanity emerged as we are. And I'll go back to this one. So this again, here's the natural variability, the green bars, and how it's changed in roughly the last 100 years. And so this, and there's no sign that we're going to change our rate of emissions for a while. I mean, there's not any evidence that any country on Earth is trying very hard to change it, and to the consternation of a lot of young people today, probably for good reason. But that's, anyway, this is just a statement of what it is. Now, what does this all mean? What do these warming temperatures mean? And I'm going to focus a little bit here at the end. I'm not a fisheries expert or anything, but I do know something about how these systems interact. And I can I'll talk first about things like hurricanes and storms, and then at the end I'm going to talk a little bit about fish populations, from which we can learn a little from the past. This is a satellite image of Hurricane Katrina, which, as we all know, affected a town along the Gulf Coast back in a few years ago, 2005. And in fact, my friends from Portland, Oregon, who are visiting here tonight, were actually connected to this part of the country in their lives, and so we're very familiar with this. But the way hurricanes work is that water temperatures higher than 80 degrees Fahrenheit lead to sufficient evaporation of water from the oceans. It all has to do with energy derived from evaporating water. Why does evaporating water matter? Well, it matters for the same reason that evaporation of water in a steam engine or any steam kind of function operates, even our tea kettles, because as the water molecules go from liquid phase to gaseous phase, they increase in volume, the same number of particles increase in volume by 1,700 times. And that's why the amount of pressure that's built up inside a steam engine in the confinement of the boiler, as the water turns to steam, the coals burn, water's added, that turns to steam, and it produces this huge pressure that drives the pistons that drive the train. Well, here there aren't pistons and trains, but the energy is released into the atmosphere, and that's exactly what leads to this fantastic high wind speed and circulating in this northern hemisphere in the counterclockwise direction, and can produce these warm, very warm, high winds. And the winds are determined essentially by the temperature of the water, the wind speeds. And it happened that the summer of Katrina, 2005, had a very unusually warm Gulf of Mexico. And that's what led to this event in late summer being such a powerful effect. And so there's one example. A few years later, we had Hurricane or Storm Sandy, which came up, didn't go into the Gulf Coast at all, but it came up across some of the Caribbean islands and then up the East Coast, causing quite a bit of damage. Then it went ashore just south of New York City, and this was when all that flooding was going on in New Jersey and parts of New York, southern New York City and everything. And high winds even up on Cape Cod. We were up there, up visiting my wife's family lived on Cape Cod, and her mother was alive at the time. I was supposed to give a talk like this to the Master Gardeners of Cape Cod that Saturday. But it got canceled because of this storm. So we thought, we've got to go out. So we went by one of the lighthouses where we knew the waves would be really high. And we got there, and my brother-in-law and I were holding my wife's mother, my mother-in-law. And her feet were just about straight out like this as we carried her along. She wasn't very heavy. I'm exaggerating only slightly. But it was really interesting. But I talked about rescheduling. But anyway, this is an example of one that got pretty far north with a lot of energy. And in fact, here's a plot of hurricanes over a number of decades, and the redder they are, the more intense they are. And of course, the most intense ones are almost always over the western Pacific, where there's much greater body of very hot water. And in the northern hemisphere, all the hurricanes veer to the right because of the Coriolis effect, and in the southern hemisphere, they veer to the left for the same reason. But what we can say about this is that as the water temperatures get warmer up the coast, from say the Caribbean to up the southeast coast of the U.S. towards New England, the longer the 80-degree water is present at the higher latitude, more intense the winds will be when they get here. And that has to be. That's the physics of how hurricanes work. And back in the ice ages, or in times when it was very cold, there were not very many hurricanes. They weren't very powerful because the waters never got warm enough. And there are some people who've studied those records. So this is something it's just a very general statement, but I think we can look for, as the oceans get warmer, coming up in the next few decades, we can expect stronger, more persistent hurricane energy reaching up until they get up in this region, unless they go ashore. Because of course, once they go ashore, there's no water to evaporate, and that's when they collapse. There's no, hurricanes basically die once they go on land because there's no more evaporated water to give that energy. That's why the land sort of shuts them down. But the ones that are out in the ocean can come up here, and we can expect, generally more, not in any given year. But. Now, one other thing I'd like to talk about at the very end, and then I'll stop. We can ask how fish populations might be affected by climate change. Well, I am not a fisheries person, and I wouldn't pretend to talk about what we can expect for the Gulf of Maine, partly because we don't know exactly. We know the Gulf of Maine is one of the very fastest warming bodies of water in the oceans on Earth. But I don't know. Fisheries are a complicated process. People certainly in this area, maybe in this room, know a lot about it, more than I do. But I can give some information from the past that I think is interesting. The first example comes from some studies we did of the presence of Atlantic salmon in Maine rivers inland. Now, the Atlantic salmon are a naturalist fish. They are out to sea. They're hatched inland. They go out to sea for several years, and then they come back and go up the rivers to spawn again. And we know that the temperatures now of the rivers in Maine, and especially south of here, the Hudson used to have salmon and so forth. They're way too warm now for salmon to go in there. But it's happening. But we know something about when salmon were present in Maine over the last few thousand years by work done on archaeological sites in Maine along the rivers of Maine. And a lot of the archaeological sites have all sorts of bones of fish and mammals that are aquatic or terrestrial, and so it's really an interesting record. But it turns out some of the ones from several thousand years ago have salmon bones in them. And these have been verified as Atlantic salmon bones, and even the isotopes present in those vertebrae that were found in the sites have been studied to be able to show that those animals went from freshwater to salt water and back. So these are clearly not landlocked salmon, they're ones that have gone through the migratory cycle. But they're not present, they weren't present all the time. I have to explain a little bit about this figure. The x-axis is time, so this goes back about 11,000 years. The hashed bar here, dash line, shows how much water is present in lakes. Part of the work we've done in our lab is study lake levels changing through time. And we know that if times are cool and moist, lake levels tend to be high. If they're warm and dry, they tend to be cool. And rivers would respond the same way, of course. And so a couple of my grad students have done some really fine work on this up in the northern part of Maine. This one happens to be from a site in not too far from Katahdin. There's another one over in Aroostook County that's similar. But what this shows is that coming into this interglacial, the lake levels were low, then they got higher for a while, then they got low again when times were warm and dry in this period, got warm, cooler again, and the lake levels rose and they fell to climb back. Well, those were done independently by having sediment cores from a bunch of different depths in the lake, and it's possible to tell whether those depths were in deep water, shallow water, or exposed, and that's how this is done. But it's very interesting because these red bars I put on here represent time periods in which archaeological sites have had Atlantic salmon bones in them. Now, it doesn't prove that there weren't other times, but it's pretty clear, at least based on this, that the salmon were present when the water levels were high, things were cool and moist in the lakes and the rivers, which are the conditions salmon would prefer, for sure. So that's one example. So we can think about, this is a kind of proxy for what might have been going on in the ocean, but it certainly affected the inland population of that important fish and how people could use it. Another final example I'll mention, some of you probably may know that some of the archaeological sites in coastal Maine, and in this part of the coast, in fact, here and out on some of the islands, have swordfish swords found in them. Now that's pretty impressive because I don't think those people were taking their canoes out to the outer banks where the fishermen would go today to catch swordfish. They had to be catching from canoes, not far offshore. And there are a number of sites, and the ones that have swordfish swords in them, and they're well preserved, date from around 3,000 years to 4,500 years ago. So this was a time when something about the ocean water close to shore in Maine was warm enough that the swordfish could come in. And there's a particular time when the swordfish, a series of temperatures rather, where they come to the surface and bask, it's called. They're sort of, it looks like they're getting suntans or something, they're not really, but there's something about the surface water temperature that suits them for whatever reason. There's several things that might be going on. But those water temperatures very likely must have been high enough for those to be in close to shore so that people could go out in canoes with spears and get them. I don't know any what the alternative would be. And so that was in this period, and it happens to be a time when the lake levels show us that it was a kind of a dry, warm time, and the lake levels were low. So that might be linked. I'm really stretching here to talk about it, but these archaeological records are crystal clear. They've been well dated, and there they are. So these are interesting insights. Now, it doesn't mean if it gets a few degrees warmer, swordfish are going to show up because they've been heavily fished elsewhere, and just like cod and other things aren't going to come back anytime soon for lots of reasons. There are a lot more than just climate that affects this. But I think these are both interesting examples from the past that show that things aren't always the same. And whether we look at marine conditions, freshwater conditions, the land, forests on the land, and certainly what the people have had available as resources up to them. So I'll stop there. I hope that this hasn't been more than 45 minutes. I know it's too long. But anyway, I'd love to have a discussion if you have any questions about any of it, or would like me to explain orbital forces. But, yes?
How do you go about dating the sediments? You showed a 1 meter sediment of lake
sediments. Yeah, that's a good question. Well, back in the 1950s, thanks to work done during World War II on nuclear fusion and fission and things like that for making the bombs, we understood a lot more about radioactivity. And a chemist named Harold Urey recognized that carbon, which has several different isotopes, a typical carbon atom has 12 protons in it, but a few have 13 and a few have 14. And 14, and this is related to bombardment from the cosmic rays into the atmosphere affecting carbon molecules and CO2 molecules in the atmosphere. So the atmospheric levels are all determined by that. And so those levels, which remain pretty constant in the atmosphere, are taken up by plants in photosynthesis. But once they're taken up, they're locked in. Well, it turns out carbon-14 has a radioactive decay with a half-life of about 5,700 years. So it's extremely useful because it's possible to measure radioactivity the carbon activity of the carbon-14 content of sediments of different ages in our cores. So we have, in the case of Sargan Mountain Pond, about almost 17,000 years of time in our core. So it's the oldest lake in Maine for sure. And but we can take sediment samples or seeds and needles and things like that from the sediment, send them to a lab, and they look at the ratio of carbon-12 to carbon-14. And if there's a lot of carbon-14 and it resembles more modern samples, we know it's only maybe a few hundred or a few thousand years old. If there's very little left, it could be 30, 40,000 years old. And in our work in Florida, the sediments go back farther than radiocarbon can date, but we can date back 40 to 50,000 years, but we have some sediments from Florida that go back more than that. And so, but anyway, we're able to send samples of the organic matter in the sediment back to a lab that can measure how much carbon-14 is in there and get the ratio. And then we know for any sample we want what its age is, with some error bar, of course. But then we can make age curves that are quite reliable. This is very sophisticated now. And we can do it on many different sites and get the same answer for the same event. So we're quite sure about that. So that's one way, and there are a bunch of other ways to do dating in geology that involve radioactivity. You know, some things, volcanic things have some things in it that are have millions or hundreds of millions of year half-life, so it's possible to date all kinds of old rocks that way. Radiocarbon organic matter can only be dated back this way for about 30, 40 or 45,000 years. As a rule of thumb, you can go back about 10 half cycles, you know, 10 decay cycles, and then there's not enough to measure anymore. It's just statistics of it. But it's really useful because our sediments in Maine only go back at most 17,000 years, so ice was here before that. And so that's how we find that out.
I think it's interesting to know that actually the carbon dioxide levels are so low now than they were in the past.
Yeah.
And we think of it as being a lot, but and it's going to
Well, it's going up
affect
fast,
things.
but
It's going up fast.
still way lower than it was before.
Right.
But you know, if you think about it, the dinosaurs were about 4 or 5 times pre-industrial levels, and we're going to get to 2 to 3. I mean, that's pretty striking, really, when you think we're getting back good chunk of the way to dinosaur time. Doesn't mean dinosaurs are coming back, but it's interesting, isn't it? I mean, it's really a huge change in Earth conditions. But you're right, that's really interesting, and the notion that back when the coal and oil beds were being formed, there was so much more carbon in the atmosphere, and the Earth had to be so much warmer as a result, creating these swampy conditions, and that's what created the conditions where the coal and oil could be stored away. We call it sequestering today. We try to think of ways to do it, but nature did it a lot, and we're just taking back a little bit and burning it. And when you think about it, what we're doing, this is what's so neat about understanding photosynthesis. It's a simple equation. We learned it in 5th or 6th grade or 7th grade, something like that. C6H2O plus 6 CO2 plus solar energy equals C6H12O6, which is glucose. And that drives all of life. That's the energy that drives all of life, essentially, except certain marine organisms that live in mints. That's the different story. But what these sugars then are turned into organic matter in plants and animals, buried in these sediments that we're now extracting. And what are we doing? We're oxidizing them. When photosynthesis pushed oxygen into the atmosphere, so we have really high levels of oxygen now compared to what were present earlier, because we took it out. I mean, we took out the CO2, but we kicked out the oxygen. That's one of the byproducts of photosynthesis, is that the O2 is released. Well, now we're taking oxygen and adding fire and combusting. We're oxidizing that respiring, that carbon that's been locked away, and it releases all that solar energy. It's actually basically solar energy. But we release it, and what comes out? CO2 and water, which are the 2 things that went in the first place. That's what comes out of fires, and why steam comes out of power plants. It's the CO2 that comes out and the water that comes out, which were just taken out 400 million years ago by the sun and put in a plant that got buried. And that's all it is. It's that simple. And there's not any doubt about it. So, you know, and it's driven a lot of changes in human civilization that, you know, I mean, we all benefit from them. We are who we are because of that whole process. So, you know, it's not, there's no way to blame anybody. You know, that's just history. It's how it is. But it puts, I think, I mean, maybe you don't agree, but I think having this longer time perspective really changes the way we understand what's happening today profoundly. And I feel that way. Most of the people I've ever talked to feel that way. Doesn't anybody want to know about orbital forcing? No, go ahead, Bill.
I'm thinking of the graph of the periodic ice ages.
Yeah.
And I don't remember the shift there, whether each ice age might be a little bit less intense, but looking at the high temperatures now, we can still anticipate a future ice age in 10, 20,000 years, but it would be less severe?
That's a great question. You know, 10 years ago, I would have said, oh, of course, we'll have another ice age. You know, this is too. But there are now really serious questions about whether we might be throwing the whole system out of whack. And it might be so warm, and the ocean temperatures are so warm, and the ice on Earth so little that the Earth can't go back into a little bit of cooling that leads to an ice age. Won't be able to do it.
But and you said that you'd take 2 minutes to explain the development of the ice age. How does that cycle occur?
Well, thank you for asking.
Orbital force.
I'm a shill in the.
I didn't even ask him to do that, but he picked up quickly. Well, this is something that has been known since 1975. It was actually predicted by, I think it was a Serbian mathematician during World War II named Milut Milankovic. And he had this idea. He knew that there was variability in the Earth's orbit around the sun and the tilt of the Earth, and that this had been recognized. But he decided to calculate all the 3 different processes that I'll explain in a second and see if they could be used to explain ice ages. And he was right on the money. It was proved in 1975. Now, 3 things are going on. First of all, there are three cycles. These are all called orbital forcing, but they're all driven by gravitational interactions of the Earth, surrounding planets, and the sun, the solar system. And one of them is called eccentricity, which is the shape of our elliptical orbit around the sun. Right now, now you remember plane geometry, probably, and you remember that an ellipse, a circle, has a single point at the center. An ellipse has 2 foci. And at one point, you knew how to calculate where that was. You probably don't know, but you did. I don't know if I do either. But the Earth is at one of those foci because our solar orbit is elliptical. And what that means is that for part of the year, the sun is far away from us, relatively. It's not vastly different from circular, but it's definitely elliptical. So part of the time we're farther from the sun, part of the time we're closer. So that affects how much solar energy reaches the Earth, doesn't it? It has to. That happens on a 100,000 year cycle. It happens. It turns out that's what that is. It's easily measurable, calculated backwards and forwards in time. It's exactly what it is. And so it depends on then when also, so that factor alone, just how circular versus elliptical the orbit is enough to change solar variability on a 100,000 year cycle. And it turns out, for reasons nobody really understands, the ice ages are 100,000 years apart right now. For the last million years they have been. And so that seems to somehow be part of the metronome. The next thing is called, on this thing here, the obliquity of the Earth's axis. And that is the tilt of our axis away from vertical. And right now it's something like 23.5 degrees away from vertical, but it ranges from about 21 to 24. And the more obliquity there is, the more extreme seasonal variation there will be. If we were just perpendicular to in our orbit around the sun, there would be no, the only variability would be that elliptical. But because we're tipped, when we are pointed towards the sun, we have summer in the northern hemisphere. At the same time, the southern hemisphere is having winter. And it flips every 6 months. But the obliquity, because it changes in degree, and it changes over a 41,000 year cycle. So that's going on in addition to the 100,000 year cycle. So you can see how these, we'd have to do a bunch of calculations now. It could be easily done on your phone, but Milankovitch did it all by hand and figured all these things out. And then the third one, which is also really interesting, is called the precession of the equinoxes. And this one has to do with the fact that the Earth is spinning daily on its axis, just like a gyroscope or a top. And most of us at some point in our life, I hope, got a gyroscope for Christmas. I always love those kind of things, or a top. And you know, you pull the string and you sit there spinning, 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 and pretty soon the axis of the thing would start to wobble, and eventually it would slow down and it would fall over. But anyway, it's that wobble, it's actually driven by the rotation of the spinning disk in the middle. And the Earth's axis does that on a 22,000 year cycle. Every 2,000 years, this does one of these rotations, even though it's spinning every single day. The Earth is spinning every day. So it's a slow process, but it's the same thing as that top in the gyroscope. And that matters because that affects when we are close to the sun, which season we're close to the sun. When are we close to the sun right now?
Winter.
Yeah, what's the date, you know?
December 21st.
No, it's something like, no, that's the solstice.
The solstice.
No, it's something like January 5th. It just happens to be. It'll be a different day in, some years. But about 11,000 years ago, it was July 5th. And so that's why, I mentioned earlier, there was a time when Maine was a lot warmer and drier and there were lots of fires. That was early after we came out of that last ice age. We were closest to the sun in the summertime. And by calculations we've made, it appears that we were about 2 degrees Celsius or maybe 4 degrees warmer in the summertime than we are now. And it would have been also colder in the winter, but the summer temperatures are what determine things like drought and fire frequency and so forth. And that's the period that prevented the boreal forest from developing, because we had pine and pines and birches and things that are fire adapted. And it was after we went through this, the cycle started to switch to being now closest in the winter. Things got cooler and moister, and pines and birches diminished. Hemlock came in, spruce and fir finally came in, and we had these boreal forests with no fires. There are just about no fires in Maine compared to any other place on Earth. And there are occasionally one, but it's usually related to people. So these three things in combination produce a calculation for, in fact, every latitude on Earth has a slightly different calculation. But we can say backwards and forwards in time when these things are, and because of those ocean sediment records that I showed in that blue curve earlier, that once they were well dated, which they were finally in the early 1970s, it was possible to go back and look at all of the variability in those ocean sediment cores. And really, anyone on Earth showed the same thing, because they're an expression of either water volume of the oceans or volume of ice on land. And here's how that works. As water evaporates from the oceans, the light carbon, carbon 12 and 13, evaporate a little more easily than carbon 14. And so those get carried in the water, fall as rain and snow on the land, stay in the ice, and the oceans become enriched in the heavier carbons and depleted in the lighter ones. But when the lighter ones start coming back in from, once the ice sheets melt and all that water goes back and 140 meters of water comes up in all the world's oceans, then that ratio changes back, And those are easily measured anywhere on Earth because it happened in all oceans. And so once that became known, and people could match up, figure out the dating of those things, suddenly it was crystal clear that what comes out statistically by analyzing the time series analysis or the spectral analysis of those ocean sediment curves are exactly these three numbers. And there was a famous paper by a couple of colleagues in science in 1975 that Hayes, Embry, and Hughes that published that paper, and it documented that this, so Milankovitch was right, this is what's going on. So now exactly why each one of those and why the cycles are now 100,000 doesn't pop out, but it's clearly they're the metronome for the whole thing. But to get back to Bill's question about the future, you see, these things are going to be going on, and they were back in times when we didn't have ice ages, when the Earth was warmer. These were still going on. And there weren't ice ages because the CO2 levels weren't low enough. They were around 300 million years ago when there were ice ages. But as we drive this up, it's quite possible that the Earth's oceans won't get cold enough and there won't be enough ice deposited on Earth. By winters will be so much shorter. We're already getting spring and falls in Maine that are about 2 weeks longer on either end than they were 50 years ago. And this continues as it happens in the Arctic more and more, which is, it appears that the Arctic will be the most strongly affected, and that has to do with the fact that as the sea ice disappears and the ocean water is water for much of the year, then that dark water absorbs a huge amount of sunlight, which delays the onset of ice in the fall by a significant amount and changes our weather patterns down here enormously, because most of the severe weather systems that reach us down here start by storms in the Arctic. When there used to be sea ice from Canada to Siberia, it was just one giant continental mass, really, as far as the air knew. But now that there's water, warm water in between, it changes everything about circulation patterns. So these things there are now, I think, legitimate questions about whether we will have another ice age in this set of cycles. And I don't know the answer, but I would have thought, just 10 years ago, I would have thought, of course we will, but I'm not so sure. I'd love to stay around long enough to see, but I would too. Plus, I get the homework off.
Well, thank you. It was a fascinating lecture. I just wondered, you're a great explainer. What of all these different variables and the many charts that you showed, what do you think is missing from the public discussion? Where if you had a moment to go and just say, all that you say is true, but this is what you're leaving out. What is this thing that people are leaving out? Why?
Well, get back to this one. This is so clear, isn't it? I mean, this is just stunningly clear. And every politician and people who are taking various sides on this have seen this. And they're not unintelligent people, but there are a lot of factors at work in their decision making. And I mean, I don't want to go into the politics of it, but clearly some people benefit by us not doing anything for a while. There are billions of dollars a year that go into somebody's pockets when they burn fossil fuel and so forth. Now, there are all kinds of arguments about reasons to do otherwise and economic benefits of doing that and economic growth that can happen. And I never make it predictions or take a side or make recommendations about policy, because I don't want people to turn me off just because I said a policy they like or don't like. I want people to understand the issue and then think about it and talk about it with their neighbors and families and try to help others. I think many people understand this fundamentally, because it is a really simple story. It's like CO2 levels are higher, the Earth will be warmer. If they're lower, it'll be cooler. And right now we're going higher fast. This figure is really striking, and we haven't quite doubled the amount of CO2 present at the beginning of the Industrial Revolution, but we're close, won't be long. And I'd be surprised if we don't triple it at least. And that has big consequences. And one of the reasons these are so serious is that the residence time of carbon dioxide in the atmosphere is measured in centuries. It doesn't, even if we stopped emitting totally today, it would be several hundred years before the system adjusted back to what were pre-industrial conditions. And so the longer we keep pumping it in and raising the levels, the more long-term implications there are for people who are around. And methane has actually a greater heat trapping capacity than carbon dioxide. But methane only has a atmospheric residence measured in months. So it's really, it has an effect where it's present, but it doesn't have the long-term implications that CO2 molecules do. So this is a challenge, and I think one of the reasons that I was really glad we had a chance to do that report for Maine is that we looked really hard at it, and it wasn't a doomsday report at all. In fact, the environmental groups got mad at us because we didn't think it sounded bad. No, what we did, we tried in every case. We had chapters about 14 different topics, that from the natural systems to economic parts of forest products industry, fishing, and all that. And all of them took as a basis for the question, assuming the warming that we laid out as just a scenario. We didn't even want to argue whether it was right or wrong. It was just a reasonably possible scenario, and not an extreme one. What would that mean for Maine's natural systems and for our economy? Well, there are all sorts of questions, but one can wonder if one puts ski areas, for example, how good is that going to be? Or if we rely on tourism and we have a month back to tourism along the coast in the summer, that's an opportunity. And which crops can be grown here or in Aroostook County? Many more opportunities. So we tried to talk in each case about challenges and opportunities. And this was just to start the conversation. We had no intention of pretending we had answers for them, but we wanted people in Maine to start thinking about this and thinking because we make decisions in society all the time that have implications decades out. Every time we build a road or put in a culvert or site a school near the coast or something like that, we're spending a lot of money, and those things will be in place for decades at least. And if we know sea level is likely to be changing, and where should we put something? If something can be flooded, and it's not just average sea level, it's flooding in winter storms typically in places like Maine that matter. That's where the real high water levels come. And we all know that can be pretty amazing. I take visitors sometimes down to Schoodic Point, or Popham Beach. Popham is another point, another similar place. But Schoodic is so amazing because up there we can park our cars and walk down the rocks to look at the birds and everything. The rocks are just totally barren of anything. There's no soil, plants, or anything else. And there are trees way up above the parking lot. And go up and walk and look in those trees. There are boulders this big in those trees. Those boulders got there because winter storms threw those boulders up in there. And you see how high above the water those places are. It's unbelievable. And when I see people who are about to buy new property along the coast, I say, pay attention. It's so nice in July, a nice calm day, and the water's across the street and all that. But these things, so the point is, we can, if we want to, think these things through and make conscious decisions where we're spending it. Bankers make decisions, insurance companies make decisions. In fact, it's interesting to me that starting back as early as the 1980s, we had insurance companies quietly coming to people in our field asking for information about all this. And hurricane frequencies and things like that. They didn't publicize it, they didn't tell anybody they were doing it, but they already adjusted their rates a long time ago because they knew all this. This meant a lot. This was really down to earth information that they wanted to know. And so anyway, I think we have a chance to help our communities think this through and make decisions that make sense. Some people don't want to face the consequences because they might be developers who own coastal property, and I can understand that. But in North Carolina, they went through a phase where there's a famous geologist at Duke who helped, Warren Pilkey was his name. He helped the whole state understand all of this, and the state passed some zoning regulation about coastal development that would require them to look at least 100 years storms and into the future for siting new buildings, because somebody always wants to build a new hotel or something, condos on the beach. So that was in place for a while. But then, you know, he's out of the picture, and I don't know, 10 or 12 years ago, the legislature of North Carolina passed a law that sea level rise is illegal. And not literally, but what they, of course they can't legislate against it, but what they legislated is against considering it in any way during planning and zoning for development. Now, how smart is that? You know, so we can do better than that. Now, Maine, we kind of have a common sense way of approaching things, and I know our surrounding states do too. And I think, you know, we just need to make sure we're trying to take this all into account. Actually, the state geologist now has fantastic records of the coastal zone all along the coast of Maine that shows vulnerability to rising sea level in every community. And that, you know, any planning and zoning that goes on certainly should be taking advantage of those. They're there to be used. And sometimes they're hard decisions, but I think most people, if they think it in a common sense way, you know, decide, you know, how about building a new school over there in that field across the road, and it's not going to be threatened or something. You know, it can be done. Often at lower cost. I mean, building on close to the water is always really expensive, almost always really expensive. So anyway, these are interesting questions, and we're all wrestling with them all the time. And I just encourage, when people ask, right, they don't say, well, we need cap and trade, or we need carbon tax, or whatever. Those are all kinds of possibilities of things that might affect human behavior. But I do think that we need to discuss it seriously, and you know, and sensibly, and not in anger, try to get people to have a serious discussion and make decisions that are proper, best for our community's future. And hardly anybody wants to make bad ones if they're just given a chance to discuss and learn. And so that's my goal in all my talks, whether it's to an oil company board of directors, or you, or the Historical Society of Eastport, is to help everybody go home understanding some of this in a slightly different way and being able to talk about it. And that's my contribution.
So are we saying that the only thing that will reverse the existing level of carbon dioxide is photosynthesis?
It can be done other ways. You know, planting trees and letting them grow will help, but that only works once. Because as soon as we cut the trees down and use them for something, the carbon's in the atmosphere. So, and in fact, Maine right now has fairly young forests, it turns out. I happen to know a lot about this. And if we did less cutting, or maybe if the markets didn't drive as much cutting for a few decades, a lot of carbon would be taken up right here. But it's still a tiny fraction of what gets put out every year from fossil fuels. And until when those trees get to be about 200 years old, they can't do it anymore, because that stops, they die, or they start falling over and decomposing, and so there's just a steady state amount of biomass in the forest, above ground and below ground. So this is, it's a good thing, planting trees and things like that matter. Back in May, I was invited down to Drexel University, which is an excellent engineering school in Philadelphia, to help teach a course in energy. It's sort of focused on coal because of that region. But it was about the science and policy of energy. And I was asked to come down to talk about the climate part of that story. So I spent about 4 or 5 days with the students. We went on a great field trip and down into Oklahoma and all kinds of things. But since they were engineers, I thought this will be interesting, because one suggestion has been that we can use an engineering solution, which is to remove the CO2 from the atmosphere using you know, chemical processes that fix the CO2, and then we can just sequester it ourselves. Okay, so I thought this through, and I talked to a colleague of mine who's a geochemist, and figured out my plan. So I said, okay, you're all engineers, most of you, and let's think about this. Many of you read John McPhee books, and there's one about modes of transportation that includes towboats on the Mississippi and trains that go from the coal mines in Wyoming out to the East Coast and so forth. And one thing that really stuck in my mind years ago when I first read it was that the low sulfur coal in Wyoming, northeastern Wyoming, that's been used since the Clean Air Act to help reduce sulfur emissions, which we have done remarkably with scrubbers and by using cleaner coal. These are strip mines in northeastern Wyoming, a few miles from where I grew up in western South Dakota. And those trains go out there, 1.5 mile long trains. They don't even stop. As they pull through the mines, they get filled, moving through, and then they drive across the country to power plants. Well, there's a power plant just north of Atlanta that serves the greater Atlanta area, which is, of course, a big metropolitan area. And this power plant now has actually 2 generators. It's sort of a double one in the same place. And that power plant is one of the sites, the targets for one of these trains, a lot of these trains from Wyoming. It's just that one place goes through, I think it's 5 or 6 1.5 mile long train loads a week. That one place. And that's all burned. They don't even stop there either. They empty out driving without slowing down. They turn around and go back uphill to Wyoming. Fortunately, downhill is to the east, so they don't have to use as much energy for the trains. But anyhow, that keeps going on and on. So that gives us at one site where coal's being burned, the volume of material that's put into the air every day. And, okay, then, well, there are engineering solutions. It's possible to have particles of bits of rock, calcium and magnesium, that are put in the exhaust stream, and those will combine with CO2 to form a carbonate that forms in some lakes and things, and then that carbonate can be put aside and sequestered, and then we've removed it from the atmosphere. So what I learned after we had extensive conversations over coffee with my friend Steve Norton, he said, well, you'd have to get the calcium and magnesium from basalt, which is a volcanic rock. And he said, and so that would have to be mined, and then ground up into flour, because it can't be chunks of rock in there. So that has to be mined, brought to the site, ground up into bits, slight bit of energy involved in all of it. And then it could be used to remove quite a bit of the carbon in the effluent. Then the question is, okay, what do we do with that? Well, it turns out that the volume of that carbonate that would be produced that way is essentially the same amount as the coal was, so they could fill up every train with that every day, send it back to Wyoming. But that, I mean, think about that. That's one place on Earth. And that's what it would take. Now, already, there are scrubbers on some places, and just the activity of having the carbon removed reduces the efficiency of combustion in those power plants by about 20% or 25%. So there's already a loss of energy in the process, but that's not even, nobody's thinking about the cost of bringing, where do you get that material and do it, you know. So think about that. And I had read some books about this a few years ago just because I was curious about it. And somebody pointed out that globally, if we could remove just this year's emissions, the powdery stuff that we'd have to do something with would fill Lake Ontario. So that's true. I mean, it has to be true. That's just the way the chemistry and volumes of things work. So it seems to me kind of impractical that we're going to do it that way. Maybe somebody will come up with a brilliant solution. There are lots of people who are trying to get investors in schemes that sound really good. And I mean, there's an ad famously on TV all the time now, in these football games and golf I watch and things like that, by ExxonMobil, and nice lady's voice saying, plants remove carbon from the atmosphere to make sugar and photosynthesis. And they show these plants. And then they say, wouldn't it be nice if our plants could do the same thing and remove carbon and make the world a better place? Well, yes, it would be nice. But it's just, I think about that, and it sounds so nice. And it sounds like they're doing it or something. Yeah. But of course, I mean, just the thinking it through and sort of the basics of the way I just described that I did for those engineers at Drexel really illustrated to me that this is, you know, energetics, all of this can't work. I mean, it has to take at least as much energy to actually remove the stuff as we got out of it. Sure. You know, so it can't, energetically, it can't be a workable solution. So I don't know what else.
We've gone a little long, so we should wrap it up. Thank you.
Thanks for your attention, I appreciate it.